Okay, um, so xp minus pf, xp minus px acting on f gives you ih bar times f, so a constant times f. And so we can say um, that um, just the this uh, relationship between the operators xp minus px is equal to ih bar. Okay, and we define the commutator of two operators as and we write it in this form: a comma b, and again sometimes we just leave off the hat, so ab is equal to a times b minus b times a. And remember, these are operators, so they're being applied to a wave function, but this commutator is just with respect to the actual operators themselves. So two operators are said to commute if their commutator AB is equal to 0. And a simple example of that would be applying the x operator twice. And we know that x, if we if we if we if we apply x twice, it doesn't matter which order we do it in; it's the same. And so we know that's going to be 0. And so um, uh, if the commutator is 0, okay, that means that we say these two operators commute, and that means it doesn't matter which order you apply them in, and that means that they're somehow independent. Okay, and even more deeply, it means that you can actually measure these two quantities at the same time simultaneously without any limitations on their mutual precision. Okay, so the fact that the commutator of x and p, xp minus px, is not 0 means they don't commute, which means that you can't measure these the physical quantities which correspond to these operators, that is the position and the momentum, with arbitrary simultaneous precision. And we know that's the uncertainty principle. And in fact, the fact that the commutator xp is not equal to 0 but is equal to ih bar, um, again means that x and p do not commute, and this is actually the origin of the uncertainty principle which we talked about before, namely this statement: delta x delta p is greater than or equal to h bar over 2. Now, showing that from this is not trivial. We won't do it, but you can but qualitatively, what you should remember is that if the commutator, if the two variables do not commute, that means that there's some limitation on on the precision with which you can simultaneously measure the associated quantities that correspond to those operators. Okay, so that's operators and a little bit about commutation. Now let's take a first peek at the raising and lowering operators. So again, we can write the Hamiltonian operator for the harmonic oscillator in this way. Okay, it's equal to 1 over 2m. It's equal to p squared over 2m plus 1/2 m omega squared x squared. And now we want to think about these p squared and x squared. These are actually operators now, but just for simplicity, I'm not writing the hats. Okay, and we just rewrite it in this way. Okay, 1 over 2m times quantity p squared plus m omega x squared. Okay, excuse me. So if p and x were simple numbers, or even if they were commuting operators, which we know they're not, we know they don't commute, then we could use sort of the general expression that if you have two numbers g squared plus h squared, you can write that as the product of plus ig plus h times quantity minus ig plus h, where I is just the imaginary number. And if you multiply this out, we see that we get g squared plus h squared. So along those lines, let's define the raising and lowering operators to be a linear combination of p and x this way, so that a plus is equal to some prefactor, which sort of makes these things dimensionless, times minus ip plus omega m omega x, and